From simply finding areas of weird shapes to essentially inventing calculus as we know it, limits have come a long way. They're a tool used to expand the possibilities of math, but what do they actually do? Well, it's quite intuitive actually. Limits describe what happens when you edge closer to a value but never hit it. Let's take this example. Let's say you're on a staircase and you want to find how high you are at this point, but you die if you hit it, making you unable to check your y value on your chords. So, to guess your y value, you could use a limit. This here is a limit. This number here describes what input, or x value, we are approaching, in this case, x equals 4. And here is a function we are finding the limit of, or the staircase. And here's the y value that we approach, or the answer to the limit. So in non-mathy terms, we can read this limit as we slowly approach block number 4, meaning we'll be on block like 3.99999, but never quite at 4, we approach the height of 6 blocks. But this only works if both sides approach the same value. For example, if we shift up this side of the staircase, suddenly approaching 4 does not make sense. If you approach 4 from the left or right side, you'll be at different heights. And so, to fix this, directional limits are used. A plus sign indicates that you're approaching from the right side, or with inputs greater than 4. A minus sign indicates that you're approaching from the left side, or with values less than the limit. Both limits have their own respective value, since the left and right side approach different heights. But while limits can calculate graphs, there's much more that they can actually do. Most notably, they can make impossible calculations possible when dealing with math that involves infinity or division by 0. Limits are truly limitless. If you were to fly in the x or z direction for an infinite amount of time, you'd eventually approach a value of 30 million, since there's a barrier at this place. However, if you were to fly in the y direction for an infinite amount of time, you would reach a height of infinity since there are no barriers to hit. That means infinity as an input, despite not technically being a number, can give an output, or a value to work with. This concept is called end behavior, and you'll likely come across this in school when a question asks what happens to a graph when it stretches to infinity. The same case is with functions with division by 0, usually when you have a function with x in the denominator. While division by 0 always leads to an undefined value, approaching division by 0 can look differently since the limit is different. And you can see this with these two graphs, because they approach dramatically different values, where this one shoots to infinity, while this one approaches 1. So, limits gets a value of a function, usually for one that's impossible to calculate, like infinity or that staircase, or for a value that doesn't exist, like division by 0. But most importantly, how is this useful, or what is this used for? Well, Archimedes, the dude from Percy Jackson, one day proved the area of a circle using an exhaustion method. He calculated the area of a shape with an infinite amount of sides, then cut up the shape into an equal amount of triangles and calculated the area of the combined triangles. By doing so, he proved that the area of a circle is pi r squared, and this calculation is still used by engineers to this day. Later, limits were used for infinitesimal calculus. Newton technically used limits before they were invented to calculate derivatives. This will make more sense if you watch my calculus video, linked above. For physics, he was able to find their speed, or rate of change of an object at a point, by finding the difference in rise and run between two points that were infinitely close to each other. This means he was able to find an object's instantaneous rate of change, rather than an average rate of change between 2 points. See, without a limit, you would get a rise over run value of 0 over 0, or undefined, since the arrow didn't move at all. So the limit allows us to see what happens as we approach a rise over run value that has inputs infinitely close to each other. This revelation by Newton created calculus as we know it today. Later, Bernard Riemann used limits to find areas of complex shapes. For curves like this, Riemann cut the shapes into rectangles. To approach the exact area, he used a limit where the width of the rectangle got infinitely skinny until he precisely calculated the area of a curve. This is called a Riemann sum, and you'll likely learn this in Calculus 1 or any introductory calculus class. The Riemann sum was used as a proof for an integral, and it gives a good visualization of what an integral does, converting from velocity to position or displacement. But while not everyone will be calculating derivatives in their daily life, if you understand the mathematical tools we are given, you too can make a contribution to our understanding of math as previous mathematicians passed the baton to us. So if you liked the video, please consider subscribing since it's the best way to help me out, and if you didn't like the video, then just tell me what I did wrong. Also, thank you for 1,000 subscribers, and I genuinely didn't think I would hit it this fast, and the support's been amazing, so thank you. I want to shout out my dad, grandma, the real man Big Noon, and